Hello everyone, how are you? We are back again on the conceptual series of entropy. This is the third session in this conceptual series, and in the last two sessions, in the first session we have talked about physical significance of entropy. Okay, what is the physical significance? How can you visualize entropy around you in the physical world? Okay, and what gives you the basis for entropy or randomness, right? That is what we covered in the first session. In the second session, which was entropy calculations, we have talked about how to express entropy in mathematical terms. So we have expressed entropy in terms of heat transfer and temperature. Okay, so you can get the links for the last two sessions in the chat box as well. If you haven't seen them, please see them so that you will be able to understand better this session. I mean, you can see that those sessions later on, okay, but that is required in order to go ahead. Anyway, so we are going to continue our session which we started yesterday of entropy calculations. A little part is left. I gave you a hint how to calculate entropy, okay, if it is a non-isothermal process. Okay, so we are going to continue with that today, and Clausius inequality we are going to see, right? So before we move ahead, a little bit introduction about myself. I have around 4+ years of teaching experience. I have done my MTech, MSc from Politecnico di Milano, Italy. I have industry experience, some research experience, as well as some research publications as well. Okay, the areas that I will be covering for your GATE exam will be thermal engineering. So thermodynamics, heat and mass transfer, RAC, power plant, IC engine, all these things I will be covering. Okay, some maybe one or two subjects or maybe more than that. Okay, so anyway, let's come on the topic of entropy. So to revise what we did yesterday, we started with entropy calculations. We came on Clausius theorem. So what did Clausius understood? What did Clausius realized? That there is a term called dq by t, and its cyclic integral is 0. So it must be a property. And we also know that entropy or randomness basically is a function of heat transfer and temperature. So we have to merge those things, and Clausius gave this dq by t term as he named it at entropy, ds. Okay, so from the Clausius theorem for a reversible cycle, we defined this. Okay, what did it define? It defined cyclic integral of dq by t is equals to 0. Then he realized that this term is ds. I have named it ds. Okay. Then from the same thing we came up to how to calculate for a reversible process. Okay. So here it is a cyclic integral. You should understand the difference. This is cyclic integral. And this is an integral for a process from initial position to final position. So I can say ds is equals to integral of initial point to the final point dq by t. You should be very careful. Both these equations are only valid for a reversible, whether it is cycle or whether it is process. It should be reversible. It should be reversible. Good evening, Surya. Okay, so basically these two equations are defined for a reversible. Now it could be a cycle, it could be a process. Now, when we talk about process, we have defined, because the integration is such that we have classified in two ways. If there is a isothermal process happening, so heat transfer is happening at constant temperature. So what can I do? I can take the temperature out. And I can write like this. Okay. So ds is equals to q by t naught. Very, very, very important. It is only valid when heat transfer is happening at constant temperature. When heat transfer is happening at constant temperature. Okay? Very important. Then the question that we left with yesterday was, what will happen if the temperature is not constant? Earlier temperature was constant, heat transfer was happening at constant temperature. So I took the temperature out and I integrated heat, dq. But if the temperature is not constant, so I cannot take this temperature out. Okay, I have to integrate it with the temperature inside. Okay, so what can I do? I can determine this dq in the form of P, V and T. Okay, so according to first law, I can say dq is equals to du plus dw, which is P dV. This is from first law. Or I can also say that dq is equals to dH minus V dP. So what will I do? When the temperature is not same, when the temperature is changing during the process, I will replace my dq by these terms and I will express. If I replace by the first equation, I can calculate ds as a function of temperature and volume. If I input dq in this term, I can express ds as temperature and pressure. Okay, so let's try to do this. Now we are talking about the process when temperature is not constant. When temperature is not constant, okay? So when the heat transfer is happening, it could be a solid body, it could be happening within a solid body, liquid body or a gaseous body. Now for a solid body, solid and liquid, for example, water is there. Okay, and heat transfer is happening in water. So in water, or for example, it's a water, okay? Or for example, it's an iron block. Okay. Now whenever either it is taking heat or it is transferring heat, because these are for solids and liquid, volume change. When the heat transfer happens, volume change is negligible. They are incompressible. Okay, so solids and liquids are incompressible and therefore dV is equals to 0. So what I am going to do, I have this equation, equation 1, and dV is equals to 0. So now I am going to replace this here. Replace this here. So what will I get? I'll get ds is equals to integral of du by t. Now we all know what is du, change in internal energy. What is change in internal energy? IF C dt by t. What is u? U is equals to du is equals to m cv dt. What is small u? Du cv dt. Because that is specific internal energy. Small u is specific internal energy. So I divide it by u. Small u is equals to capital U by m. Okay. So I have this now. Now C I can take out. This C is constant. Is a specific heat of that solid or liquid. It is specific heat. C is the specific heat of that solid or liquid which we are talking about. Now basically, you know, if I talk about in practical terms, C basically changes. Specific heat changes with temperature. But for most of our calculations, we assume that it is not changing. C is constant, we take it as an average temperature. So C we are assuming as constant, C will come out. And you will also have to take C constant for all your calculations. Okay. So C I can take out and I will integrate. I can take C out, initial to final, dt by t. And when I integrate this, we all know what happens. We all know what happens. What? C ln T2 by T1. This is the integral. Okay. So if they will ask you that tell the change in entropy when the system has a liquid or a solid, then you can calculate using this. Now there is a point here, very important point. What? When I say ds is equals to initial to final dq by t, now it is only valid for a reversible process. It is only valid for a reversible process. Then I replaced dq from du plus pdv. Now tell me. And I got the equation ds is equals to integral of if du by t. Now this is also a property. U is also a property, T is also a property. Now the whole equation is determined in terms of property. And property for a reversible process or for an irreversible process, so change in property will be same. It does not depend on the path that you are taking. It only depends on the initial and final point. Whether the path is reversible, whether the process is reversible or irreversible, it does not matter. As long as the initial and final points are same. So change in property will not change. So if I talk about this equation, it is only valid for a reversible process. But when I talk about this equation, it is valid for reversible as well as irreversible process. Why? Because this dq that was there is replaced by internal energy and pdv. I have replaced dq in terms of properties. So dq is a path function. dq will be different if it is irreversible or reversible process. But internal energy or any property, its change will be same. It does not depend on the path. If the initial and final points are same, change in property will be same. So what should I know till now? I should know that if the temperature is changing and I have a solid or a liquid, I can calculate entropy by this. Okay. Now, what about gases? Solid, liquid I have covered. What about gases? So there I can use ideal gas equation. I can assume it as ideal gas. Okay. So this is a general equation. Now I don't think I need to tell you this. This is a general equation. This is your first law of thermodynamics for a process, for a closed system. Now let me replace this dq here. As soon as I replace dq from this equation, earlier that equation is only valid for reversible process. As soon as I replace dq from du and pdv, I get this equation. And now entropy is a property, u is a property, t is a property, p is a property, v is a property. This whole equation is in terms of property, and therefore whatever I get from here, it will be valid for a reversible as well as irreversible process, as long as their initial and final points are same. Okay. So now let me integrate this. When I integrate this, I will get du is equals to, we all know cv dt. Okay. And pyt for ideal gas, what happens? PV is equals to mRT, right? So let me replace P is equals to mRT by V. Now I can replace P here, okay? So I can replace du by CV dt by T, plus let me replace P mRT by T dv by v. I know there is little, like its space is not enough, but I'm sorry for that, okay. So this t and t will get cancelled and m will not come here, I'm sorry, m is 1, okay. So I'll get here r dv by v, r, you will get this equation. And you all know integration. So S2 minus S1 is equals to CV ln T2 by T1 plus R ln V2 by V1. Now this equation is very important. If temperature and volume is changing, in a ideal gas is given and temperature and volume is changing, you can calculate entropy by this. Same thing you are going to do with this equation. You are going to replace this here. You are going to replace this here, and now this is only valid for a reversible process and this is valid for both. Okay, so same thing you are going to do. You are going to integrate this and you will get this equation. Okay, now these two results are very, very, very important. These two results are very, very, very important. Okay, so these are valid for reversible as well as irreversible process. Okay, now before, instead of wasting a lot of time on the equations and theory and all, let's try to solve a question so that we can get the clarity of the concept. Okay, now, so what do I have? I have water here. Okay, I have water here at 27 degrees Celsius. So let's say 300 degrees Celsius and 1 atmosphere. Now I am giving heat. And I have thermal reservoir here. Thermal reservoir, let's say at 600 degrees Celsius. And I am giving heat. When I am giving heat, this water will convert into vapor at, let's say, 400 degrees Celsius. 400 degrees Celsius. So first of all, water. So what will happen here? We all know this diagram. This is phase diagram. Okay. So this is 300 degrees Celsius. Water is in liquid form. Water is in liquid form. Okay. Then I am giving heat. I am giving heat and it will go to 373 Kelvin. I am sorry, this is Kelvin. Okay. Okay. So it will go to its boiling point. It will go to its boiling point, and then it will convert into vapor. So here I am going to give latent heat, and it will convert at the same temperature, at the saturation temperature, into vapor, and then it will go up to 400 degrees Celsius. Now this is vapor at 400. Okay, this point is 1, water at 300 degrees Celsius, and this is 2, this is 3, and at point 4 we have vapor at 400 degrees Celsius. This is what I have given in question. Okay, now they are asking first, tell entropy change. Calculate entropy change. So entropy change you need to calculate. But entropy change of what? What do you want to calculate entropy change for? So let's take A for water. When water changed at when I am giving heat, water was at 300 degrees Celsius and it changed to vapor at 400 degrees Celsius. 300 Kel. I'm sorry. I'm very, very sorry. Okay, so water was at 300 Kelvin and it changed into vapor at 400 Kelvin. What is the total change in entropy? Okay, so how you are going to do it? So first of all, you see what is the total change that is happening. First of all, this change is happening, entropy 1, change in entropy 1. Then this is happening, entropy 2, and finally this is happening. So I need to calculate for delta S1, delta S2 and delta S3. Okay, if I am focusing on water. So I have taken this as my system and they are asking, tell us what is the entropy change in this. Okay, so how do you calculate delta S1? First condition, it is liquid. It is liquid. Okay, and the temperature is changing. What do I know? How to calculate change in entropy when temperature is not changing and when temperature is changing. When temperature is changing, then how to calculate for a solid or a liquid and how to calculate for a gas. So this is the case when temperature is changing, but in liquid. So I already talked about that, and that is MC ln T2 by T1, isn't it? This is what we calculated. Okay, so tell me, we are taking 1 kg of water into, what is the specific heat of water? The specific heat of water is 4.18 kilojoule per kg Kelvin, and ln T2 is 373 by 300 Kelvin. You should always put it in Kelvin. So if you calculate that, I am not calculating it, okay? Okay, let me just 373 by 300. Can you tell me how much is it? Can someone tell me how much is it? Yes, I have corrected that, Bhavya. I'm sorry, I wrote it by mistake. Okay, so yeah, this is also in Kelvin, I'm sorry. So this is 0.91 kilojoule per Kelvin. This is delta S1. Second, delta S2. Now tell me what is happening here. Now here water is converted into vapor at the same temperature. So I am giving heat at the same temperature. So this is isothermal heat transfer. And I know if I need to calculate isothermal heat transfer, I can directly write Q upon T naught. Now what is this Q? Mass of water into latent heat of evaporation. Latent heat of evaporation upon temperature at which the phase change is happening, the constant temperature. So 1 kg into 2257 kilojoule per kg, and what is the temperature? Temperature is 373. So if you calculate it, you will get 6.05 kilojoule per Kelvin. Okay, let me write it here. Okay, and finally I will calculate delta S3. How will you calculate this? What is this case first of all? Here temperature is changing. What is the phase? Gas is the phase. And how is it, when the temperature is changing, I can use two equations, either temperature and volume or temperature and pressure. So let me write temperature and pressure. Can I write M Cp ln T4 by T3 minus R ln P4 by P3? Yes, I can. But when this heat transfer is happening, it is happening at constant pressure. This is the constant pressure line, okay? We all know that this heat transfer is happening at the constant pressure, okay? So, pressure is same. So, this will go to 0 and I will left with 1. Now, this is Cp of vapor, water vapor, because it is gas. It is in gas state, okay? So 1 into 4.18. Okay. I think I need to rub a little bit here. So it is 1 kg into 1.996. Okay, I can't write it here. Okay. Let me remove this. So this is delta S1 and this is delta S2, okay? And delta S3 I can calculate 1 kg into 1.996 kilojoule per kg Kelvin into ln 400 by 373. Okay, so kg and kg will get cancelled and you will get 0.14 kilojoule per Kelvin. Okay, okay, right. So they were asking for water. They were asking for water. I will tell you what is entropy change for water. Entropy change for water is delta S1 plus delta S2 plus delta S3. Okay? And when you sum all of them, you will get 7.09 kilojoule per Kelvin. Okay? So this is the first thing. They have asked the entropy change for water. I hope you are able to calculate this, okay? Now let's take another case. Let's take another case. So let me, delta S2 is equals to 6.05 kilojoule per Kelvin, delta S3 is equals to 0.14 and delta S of water is equals to this. Now what if they are asking for this thermal reservoir? Entropy change they have asked. First they have asked for water. This is what I am doing by myself, okay? Let's say they are asking for water, so I have calculated. Now they are asking, tell me what is the entropy change for thermal reservoir. So what is thermal reservoir doing? It is giving you heat at constant temperature. It is giving you heat at constant temperature. We all know how to calculate entropy change when heat is transferred at constant temperature. Q upon temperature of thermal reservoir. Okay. Now temperature of thermal reservoir I know, but how do I calculate Q? So I need to calculate what is the total heat that is given. So what is the total heat given? Q is equals to Q1 plus Q2 plus Q3. What is Q1? Here Q1 and here it is Q3. So Q1 is M into Cp of water T2 minus T1. Isn't it? I am giving heat to water. Then here Q2 is what? M into latent heat. And Q3 is what? M Cp of vapor into T4 minus T3. So you can put it here. 1 kg. This is 4.18. And T2 is 373 and T1 is 300. So this is 73. Plus 1 into 2257 plus this is 1 into 1.996 and T4 is 400 and T3 is 373. So this is 27. Okay. Yes, what is the confusion? What is how, sir? Surya, is there a confusion? Okay, you can write it down. I'll check it later, okay? Yeah. So when you calculate heat, total heat, you can calculate it and you will find that it is 2616 kilojoule. 2616 kilojoule. So let me write it here. 2616 upon temperature is 600 Kelvin. This is in kilojoule. This is in Kelvin. So what will I get? And very important thing that you have to remember here, that this Q is the heat that is given by the system. This Q is heat given by the system. So what will I write here? For the system it is positive. If I talk about this, it is positive. But for the thermal reservoir, it is negative. Okay, so this is negative here. Okay, I am giving this heat to the water. Thermal reservoir is giving this heat. Okay, so the answer that you will get is minus 4.36 kilojoule per Kelvin. Minus kilojoule per Kelvin. So now you have seen, that is why in the last session in the beginning, I told you that you need to differentiate between what is your thermal reservoir, what is your system, what is the process, what is the cycle. Now if I ask you, tell me the total entropy change in this process. So what is happening? In this process, thermal reservoir is giving heat to the system. So the entropy of the system is increasing. How much? Plus, this is entropy change of water. So water is your system, isn't it? So entropy change of the system is increasing. Entropy change of the reservoir is decreasing. So if I ask you, tell me the entropy change for a process. So what will you do? You will sum them all. Okay. So if I ask you, first I talked about entropy change of water. Then second I talked about entropy change of thermal reservoir. Now tell me what is the entropy change during this process. Total entropy change. So entropy change during this process will be entropy change of the water system plus entropy change of thermal reservoir. Now, entropy change for water was how much? 7.09. For thermal reservoir it is minus 4.36. So in this process, how much is the entropy change that is happening? It is 2.73 or 74, yeah. That is correct, Bhavya? Yes. Okay. Okay. Now I can give you, look, I have whatever we are covering yesterday and today, till now. I have not come on Clausius inequality as of now. But this question is going to give you complete clarity of what we have done till now. Okay. Now I take one more example. There I was giving heat from a thermal reservoir. Now let's assume I am not assuming a thermal reservoir, I am assuming a thermal body. And the temperature of that thermal body, for example, iron block is there at 600 Kelvin instead of the thermal reservoir. Okay. I am assuming that is a thermal body. And its temperature is changing from 600 to 500 Kelvin. So now I cannot calculate as I calculated earlier. Now I have to take the case of non-isothermal process for a solid body. So how can I calculate? Delta S of thermal body will be equal to mass of that, for example, it's an iron block. So mass of that iron block, specific heat of that iron block, ln T final by T initial. Okay. So mass would be given you in question, okay, whatever it is. This will also be known to you, ln 500 by 600. So you will get entropy change. So see how in a same question, how many variations could be asked. Okay. So now you know how to calculate the entropy change of your system, how to calculate entropy change of thermal reservoir, how to calculate entropy for the whole process, how to calculate entropy if the temperature is changing. So thermal reservoir is not there, but thermal body is there. Okay. So is it clear? I hope it is clear. Okay. Okay. So let's move ahead. Let's move ahead. Okay. This is, I have left a slide so that I will need some space for solution. I don't need it now. Okay. Let's go to Clausius inequality. Clausius inequality. Okay. We will go a little fast because this I needed to cover, but that question was, very important. It covered all the things that we have done till now. Okay. So Clausius inequality says, look, Clausius theorem says dq by t is equals to 0 for a reversible cycle. Okay. And Clausius, this is said by Clausius theorem. Now Clausius inequality said that this entropy will never, this dq by t will never be greater than 0 for a cycle. Okay. So for a cycle, cyclic integral of dq by t is always less than equal to 0. It is always less than equal to 0. Okay. This is Clausius inequality. Okay. For a reversible cycle, if it is a reversible cycle, I already know this. I have already proved this by Clausius theorem. But if it is an irreversible cycle, okay, so it is dq by t less than 0. dq by t, cyclic integral of dq by t less than 0. Then it is an irreversible cycle. If cyclic integral of dq by t is greater than 0, then that cycle is not possible. Then that cycle is not possible. That is Clausius inequality. Okay. Very fast, very quickly we will see this question. We have a heat engine and we are giving heat at 327 degrees Celsius. So 327 plus 273, 600 Kelvin. I am giving heat 420 kilojoule. Okay, 420 kilojoule I am giving. Then I am rejecting also heat. Q1 and Q2 is rejected at temperature 27. So this is 300 Kelvin, right? 273 plus 27, 300 Kelvin. Okay. Now I don't know what is Q2. Now Q2 can be A, B or C. Now they are asking, tell if this cycle is possible or not. If it is possible, then it is reversible or irreversible. Okay. So let's take case 1. Cyclic integral of dq by t is equals to q1 by t1 minus or plus q2 by t2. But I need to put minus here because it is rejecting heat. Okay. So Q1 is how much? Q1 is 420 and 600 plus minus 210. I am taking the case A. Okay. Upon 300. So how much is it? Can you tell me? This is 0. So what can I say? What can I say? This is a reversible cycle. Reversible cycle. Okay. In the second case, this is case A. In case B, can I take cyclic integral of dq by t is equals to 420 by 600 plus minus 105 by 300? Yes, I can. So how much is it? Can you tell me how much is it? This is plus 0.35. Now tell me, what did I tell you? Cyclic integral of dq by t will be less than or equal to 0. It cannot be greater than 0. In a cycle, dq by t will always be either less or equal to 0. This is greater than 0. So this is impossible. Very nice. Yeah, Surya, that is first one is reversible and this is impossible or not possible. Yes, okay. And the third case you can calculate by yourself. 420 by 600 plus minus 315 by 300. So when you calculate it, it is how much? Minus 0.35, and that obeys our cyclic integral of dq by t. That does not violate the Clausius inequality. So cyclic integral of dq by t is less than 0. So it is an irreversible cycle. It is a irreversible cycle. Okay. So I hope that is clear. Yes, second is not possible and third one is irreversible and possible. Okay. Bhavya, yes, third case is irreversible, second is not possible. Yes, correct. Okay. So it's good that you are solving it by yourself. Okay. Now, Clausius inequality is stated as, there is not even 1 second is required for this question. What is the answer? Tell me very fast, very quickly tell me. Clausius inequality is stated as, yes, it is option D, dq by t. Cyclic integral of dq by t is less than or equal to 0. Okay. Yes, by that is correct. Option D is correct. Okay. For a real thermodynamic cycle, real, and all real cycles are irreversible. Okay. For a real thermodynamic cycle, which one of the following is correct? Which one of the following is correct? So, what is the option? What is the option for this? It is, yes, Surya, that is correct. It is D. So, for D was the correct one for last one. Okay. Here, cyclic integral dq by t for real thermodynamic cycle is less than 0. Okay. So, this is the correct option. Bhavya, yes, it is option B. Correct. Okay. Now, I am giving you one question to solve. Okay. So, you try this question, you pause, when you see this, again, you stop it here and try to solve this question. Okay. This is a homework for you. You have to calculate the quantity cyclic integral of dq by t. Okay. And it's a simple question. Okay. I am giving heat at 1000 Kelvin 600 kilojoule is giving, and at 300 Kelvin 450 kilojoule is rejected. Okay. And some work is obtained. Anyway, calculate cyclic integral of dq by t. That is need to be calculated, and calculate efficiency. Efficiency is work upon Q1. Okay, this is Q1 and this is Q2. Try to solve this. Okay. Now, so it's almost time. What we have discussed today, we have discussed Clausius inequality for a cycle. Okay. So let's not start Clausius inequality for a process today. Anyway, it's not very tough. Okay. It's the same concept as we discussed in a cycle. Okay. So let's not start this today. We are going to continue from here tomorrow. Okay. So till now we have discussed what? We have discussed how to calculate entropy change. And today that question was really important. Please go to some reference book, refer some reference book, and try to solve similar kind of questions. Because if you are solving previous year questions, you will cover only one concept in one question. Okay. So when you are in the in the beginning of your preparation, when you have covered a concept, you go back to some reference book. Okay. Because in a book When you are referring a book, in the same question, you will get 3-4 concepts in the same question. Okay, so go to some reference book, pick out some entropy questions, try to solve them. Okay, make your knowledge precise. Read the question at least 3 to 4 times before solving it, so that you pick up the very important words. Are they asking entropy change for a cycle? Are they asking entropy change for a system? In the process, is it isothermal process? Is it non-isothermal process? Is it thermal reservoir or thermal body? Is it a solid or a liquid or a gas? Okay, so try to solve. You should be able to identify the key words inside the question. And then you should be able to visualize which formula to apply. Okay, so I ask you to try some questions from some reference book. Okay, and we are going to take entropy change or Clausius inequality for a process from here tomorrow. Okay, we will start from here. Okay, so I'm going to see you tomorrow at the same time at 6 p.m. here again, and we will start from here, and we will also discuss the entropy principle, increase in entropy. Okay, so that is what we are going to start tomorrow, and I'm going to see you there. Thank you very much.